So today we're going to talk about the natural logarithm, and specifically its role in calculus. So remember from algebra the following equivalence. So if y is equal to a to the power x, that is the same thing as saying that the log base a of y is equal to x. These are the same expression. And in algebra, this is typically how the logarithm was defined. The logarithm was defined such that these two expressions were equivalent. The way I like to think of it is that the base of the logarithm is a, the base of the exponent here is a, so it's a to the power x equals y. I sort of do this circular motion here. In any case, that's what a logarithm is, if you've forgotten. So, for example, the log base 2 of 8 is equal to 3 because the equivalent statement in exponential notation would be 2 to the power 3 equals 8, which is self-evidently true. Similarly, the log base 10 of 100 is 2 because 10 to the power 2 equals 100. Now, the reason that we are interested in logarithms in the first place is because you can prove that they have a number of useful properties which we can use to solve equations. So, doesn't matter what the base is, if you have a product inside of a logarithm, that product gets turned into a sum, division gets turned into a subtraction, and exponentiation gets turned into multiplication. These properties are super useful in general. For instance, you can use them to solve equations when the variable that you want to solve in is stuck inside an exponential position. So for instance, you may remember from compound interest, which was another topic that you probably saw in algebra, this equation here. I forget exactly what each of these terms means, but whatever. Say that you are interested in solving this equation for the variable r. Well, we could use these properties of logarithms to do it. Even though logarithms aren't present in this equation at the outset, you can introduce them so as to take advantage of their properties. So, for instance, one thing that you could do is divide both sides by p first, and then take the logarithm of both sides. Doesn't matter what base it is, I just pick 10 because. Well, on the right then, we have an exponential phrase inside of a logarithm, and consequently, we can pull that exponent out front, which is exactly what we've done here. So to solve for r, all you need to do is divide both sides by this big chunk, and you're done. So if you have a calculator that knows how to compute logarithms, then you know what this number r is, given the data for everything else. So that's why we're interested in logarithms. Well, it's at least maybe one reason that we're interested in logarithms. So, there are two special logarithms which are so common in applications that they have their own buttons dedicated to them on calculators. So these are the common logarithm, and that's the logarithm base 10. That's typically regarded as just log, without any base written. So on your calculator, when you see the button that just says log, really that's the logarithm base 10. Then there's the natural logarithm, and that's typically denoted by ln. You also have a button for this on your calculator. And this is the logarithm base e. E is Euler's number. It's approximately 2.71828, but it's irrational, which means that, like the number pi, it goes on forever and doesn't have any repeating pattern in its decimal expansion. Now, maybe your education in algebra was a bit different, but when I took algebra in high school, I remember being intensely confused by this. I understand that we have logarithms, and they can be to any base, and we can use them to solve equations. I understand that. But what is it about this number e that is so special that we would take it to be the base of a logarithm? What good is that? Why is this so common that we have buttons on our calculators dedicated to it? Surely the logarithm base 10 is just as good. Why is this called the natural logarithm? What's natural about this? This seems like a really strange and arbitrary choice. And as far as that goes, what is this number? Where the heck does it come from? And what is its connection to logarithms and exponents? So, the number e is very fascinating to me. A lot of people who are into mathematics, say that pi is really cool. Pi has a lot of popular support. There's Pi Day and whatever. It's popular enough that, you get people posting about it on Facebook. For my money, I think e is the much, much, much more interesting number. But that maybe just reflects my own bias for calculus and like applied mathematics things. Because as it happens, to properly explain, at least in my opinion, where the number e comes from, you need to look at things from a perspective that only calculus can afford. And I hope that that's what I'll be able to do in these next couple sections, is to adequately explain precisely what is natural about this, and why do we care at all about this number e? Where does it come from? For example, and I mean, there's more than one answer to where the number e comes from. For instance, you may have seen it referred to as this limit, which, as it happens, also becomes this thing, 2.71828. This has a significance because this limit shows up in interest theory. You may remember the idea of continuously compounded interest, where the number e shows up as a result of this limit. But we're going to take a different approach. And in the meantime, we will also introduce the calculus of logarithms and exponential functions. So at the very least, what I want you to take from these next two sections is ideas for how you differentiate logarithms, how you integrate things which might have logarithms in them, how you differentiate exponentials, and how you integrate exponentials. At the very least, that's what these next couple sections are about. But I hope I can tell a story about the mystery behind this number e as well, because that's a personal. That was a thing of personal interest to me. Back in high school, I really had no idea what it was about this number e, and that sort of really didn't take until I was outside of calculus and just sort of studying stuff on my own for me to really give myself a satisfactory answer as to where it comes from. Anyway, so here's my take on this whole situation. Let's forget for a moment everything we know about exponentials and logarithms, and let's look at something completely different. The power rule for antiderivatives has a hole in it. So recall the power rule. If you're anti-differentiating a power function, you add 1 to the exponent and then divide by the new exponent. Easy, right? You can do that with anything, as long as that exponent is not -1. Now, it's clear, after a moment's thought, why n can't be -1. I mean, what if it was? Because then we would have -1 plus 1, which is 0. So if this was -1, the power rule would ask us to divide by 0, which is clearly incompatible with reality. So that means the power rule has a hole in it. It can deal with all exponents except for -1. So x to the power -1, remember, is just the reciprocal. So the power rule does not know how to deal with this antiderivative. But that doesn't mean that we can give up. It does not mean that 1 over x does not have an antiderivative. In fact, the fundamental theorem of calculus, the first form, the content of that theorem is basically just the statement that all continuous functions have antiderivatives. That's actually what the definite integral is. That's one way of interpreting the definite integral, that is the operation that constructs antiderivatives. So the precise statement of it is here. If a function is continuous on an interval, then the function big F, defined like so, is an antiderivative of it. So notice this is a little bit weird. the input for this function is actually the upper limit of the integral. So the upper limit of the integral here is actually the variable, and the variable of integration is something completely unrelated. Now, the function 1 over x, which is what we're trying to find an antiderivative for, because the power rule doesn't supply it, the function 1 over x is continuous. It's continuous everywhere except at 0, because there it tries to divide by 0, so we have problems. So, if we let a be any interval which does not contain 0, then this function, where f is 1 over x, is an antiderivative. Well, let's make a specific choice of, let's make a specific choice of data, and then define a new function such that it is an antiderivative of 1 over x. We are going to pull an antiderivative of 1 over x out of thin air. Well, not out of thin air, out of the fundamental theorem. And this is what we are going to call the natural logarithmic function. So we have made no reference to exponents now. We have made no reference to logarithms as they were defined back in algebra, right? We have made no reference to this. All we have done is we have defined a function who is an antiderivative of 1 over x, right? By definition, the natural log is an antiderivative of 1 over x. That is what it is, by definition. And then by some remarkable coincidence, as it happens, this function turns out to be a logarithm in the traditional sense. That's amazing to me. That was something that truly mysterious and incredible, that two things which are seemingly completely unrelated actually turn out to be the same. This idea of anti-differentiation and this idea of exponents and logarithms, there is this invisible bridge connecting them that is really unexpected. So yeah, we can define the natural logarithm in this way. And don't stress too hard about this actual literal formula. It doesn't really matter. All that you should remember is that the natural log is defined to be an antiderivative of 1 over x. That is its definition. And then, amazingly, that function also turns out to be a logarithm. So, based on this definition alone, there are some things that we can say about this new function, ln. It is continuous, it is differentiable, and its derivative is 1 over x. Again, this was the case by definition. I should point out that this is only well-defined for x greater than 0, for positive x's, because if x is 0 or if x is less than 0, then this interval would be crossing an asymptote, and we don't want it to do that. So yeah, like I say, it is undefined for x less than or equal to 0, so log can only take in positive numbers. If x is between 0 and 1, then the log is negative. If x is larger than 1, then the log is positive, and the log at 1 is 0. So all of this information is reflected in the graph of natural log x, which let me go ahead and show you that. I'm certain that you have seen this before in an algebra class, but there you go. So here you can see what I'm talking about. So log at 1 is 0. Everywhere to the right of 1, it is positive. Everywhere to the left of 1, it is negative. And 0 and to the left of 0, it doesn't even exist. So it's only defined for positive numbers. You can also see that as we approach 0, the natural log plummets to negative infinity. It's a bit harder to tell, but as it happens, as we go out to positive infinity, this dude actually does grow to positive infinity. It looks like it may be approaching a horizontal asymptote, but that's actually not the case. This does go to positive infinity, albeit very, very slowly. And we can prove that. We can prove that without much difficulty. Okay, so I say a little bit more about the definition of the log function. You can read this if you want. I mean, of course, this is all in the notes. You can read this if you want. I don't think I'm going to talk about it in the lecture because we have a lot of examples that I need to do. But yeah, just remember that the natural log is defined to be the unique function with domain the positive numbers whose derivative is 1 over x and for which the value at 1 is 0. That is literally what the natural log is. And that is the sense in which it is natural, because it comes from, I would think, the very natural desire to fill in a hole in the power rule. And then the fact that it turns out to agree with the previously established notion of logarithms is, I think, a remarkable coincidence. Anyway, so here I prove that it is unique. It is the unique function satisfying these things. Whatever. So these are the laws that we would expect a logarithm to have. So it takes a product, turns it into a sum, takes a division, turns it into a subtraction, takes an exponent, turns it into a multiplication. We would hope that, I mean, by calling this thing a logarithm, we would hope that all of these properties remain true. And indeed they do. Which is also kind of remarkable to me, because we have defined this thing to be a definite integral. We have made no reference to exponents, and yet, well, all of these expected properties end up happening as well, or end up holding. So again, you can read the proof. I only proved this first one if you want, but I would rather use the lecture time to do examples. The proof follows from uniqueness, by the way. So what I do is I define this function, log xy minus log y, where y is a constant, and basically I show that f, its derivative is 1 over x, its domain is the positive numbers, and its value at 1 is 0. But the natural log is the only function with those properties. So that means that this thing has to be equal to the natural log. And so the property follows. And you can prove the rest of those in the same way. Anyway, this is the sort of stuff that you'll actually be expected to do in your homeworks and in your exams, the material of these examples. So let me spend some time on that. And I'm hoping that most of this is going to be review, because again, working with the laws of logarithms is something that you would have done in algebra. Okay, so expand this expression using the laws of logarithms. So let's see. We have a subtraction, or we have a division, and we know that division turns into subtraction. So the very first thing we can do, for sure, is turn that division into a subtraction. Okay, what else can we do? Well, here we have a multiplication. X squared plus 5 to the power 4 times sine x. Well, multiplication turns into addition, so we can split that apart as well. And there's one more thing that we can do. We have an exponent here, and by the laws of logarithms, you can take an exponent and pull it out front. So let's take this 4 and pull it out front. And then let me just copy paste everything else, because there are no more changes that I can make. And indeed, that's the farthest that we can take it. This addition inside of the log, can't do anything with it. There are no laws of logarithms that respect addition. Similarly, this sign, nothing we can do. This addition, nothing we can do. This exponent, nothing we could do. If this was just log x squared, like end parentheses right here, then we could take the 2 out. But it's not, so we can't. I don't want to see you making the mistake of taking this 2 and pulling it out. You can't. That's not how the laws work. We could do the laws of logarithms in the opposite direction. So instead of taking one big logarithm and splitting it apart, we could take a fractured expression like this and compress it into a single logarithm. So, for instance, here we have a 1/2 in front of the log. Well, I can pull that inside and turn it into an exponent. Like so. This addition, I can turn that into a multiplication. Like so. And then finally, if you want, we can just rewrite that power of 1/2 to be a square root. So, just a reminder that powers of 1/2 are indeed the same as square roots. So this function, ln, which we defined to be an antiderivative of 1 over x, with a couple other properties, at 1 it has to be 0. As it happens, this completely new function satisfies all of the properties that we would expect of a logarithm. So, if this function ln is a logarithm, it would have to have a base. So, what is the base? Now notice that if we were taking an ordinary logarithm, like log base a, that would satisfy the identity log base a at a equals 1. And that's because a to the power 1 equals a. So whatever the base is, it would be that number which, when you plug it into the logarithm, you get 1 out of it. So the base of ln is exactly that. It is that number which, when you plug it in, you get 1. And that is how we are going to define Euler's number. That is where Euler's number comes from. It is the unique number whose natural log is equal to 1. And that's not a circular argument, because the natural log was defined up here, right? Again, no reference to exponents being made. Okay, so I already mentioned this when we were looking at the graph, but the limit as x goes to infinity of log is infinity. The limit as we go to 0, from the right, of course, because only positive values of x are allowed, is negative infinity. And then I prove that. So, whatever. You can read that if you want. Okay. Differentiation. So let's differentiate this function. So we know that by definition, the derivative of log is 1 over x. So here we're going to have to employ the chain rule, because we have a function inside of the log instead of just an x. So employ the chain rule, I say. So first off, differentiate the log. That just produces 1 over whatever was inside. Whoops. So in this case, that's 1 over x cubed plus 1. But then by the chain rule, we have to multiply that by the derivative of x cubed plus 1, which is 3x squared. So, yeah, I may as well just put that on the top of the fraction here. So that's easy. Basically just, drawing your attention to the fact that you have to use the chain rule if there is stuff inside of the log, which is exactly what I note down here. So if you are differentiating a log of stuff, then that is the derivative of the stuff over the stuff itself, right? So log of x cubed plus 1, differentiate it. It is the derivative of x cubed plus 1, 3x squared, over x cubed plus 1. So that's easy. Find the derivative of log sine. Well, again, it is the derivative of sine, which is cosine, over, sine. Oh, and that's interesting. Cosine over sine, that's the same as cotangent. So that's neat. So I suppose if you were interested, we could draw a conclusion from this, namely that the antiderivative of cotangent is log sine. So let's just make that observation. So if you ever if you ever wanted to know what the antiderivative of cotangent is, well, there you go. It's got a natural log in it. Ooh, you know what? Maybe I shouldn't say this yet. So very technical, very technical point here. When you are taking antiderivatives, you want the antiderivative to be as generic as possible. You want it to have the biggest domain possible. But here's the thing. The natural log is only defined for positive numbers, right? So when the natural log arises as the result of an antidifferentiation, by convention, we put absolute values there, just to make sure that it's always defined. Subtle point. So I think I mentioned that down below. Yeah, I mentioned that in the next, after example 7. Anyway. So differentiate square root log x. Okay, so again, this is an example of the chain rule. Here we have log x to the power 1/2. So there I am differentiating the power 1/2, right? That's a 1/2 up here, so bring down the 1/2 and then subtract 1. 1/2 minus 1 is negative 1/2. And then by the chain rule, we have to multiply by the derivative, oh my goodness. We have to multiply by the derivative of log x, which is just 1/x. And I guess we can clean that up if we want. Let me write that as 1/2x root log x. Yeah, that's a bit nicer looking. Right, because this power negative 1/2 is the same as 1 over square root. So that's that. What about this dude? So once again, we have a natural log of stuff, and we're differentiating it. So we could just employ this rule. You know, take the derivative of everything inside, and then divide by everything inside. But I would have to use the quotient rule, and I don't really like the quotient rule. So you know what we can do instead? Let's use the laws of logarithms to expand this expression first, and then differentiate, because that's going to make things tremendously simpler. Okay, so we've got a division. So this becomes log x plus 1 minus log root x minus 2. But now, notice, a square root is a power of 1/2. And if you have an exponent inside a log, you can bring that out front. So this power of 1/2, I can bring the 1/2 out front. So this is, in fact, oh my gosh, I swear my typing gets worse every... Oh, how do I keep doing it? Why? It's shameful how bad at typing I am. I'm 31, like it's only gonna get worse from here. Okay, alright. Successfully expanded. Nothing else we can do. This sum, no laws of logarithms for that. This subtraction, no laws of logarithms for that. So this is as simple as we can get it. So now differentiate this simplified expression. So derivative of log x plus 1. So that is the derivative of x plus 1, which is 1, over x plus 1. The derivative of this is derivative of x minus 2, which is 1, over x minus 2. And then let's just go ahead and combine with that 1/2 there. Why did it do that? There. So that's it. So that's all we can do. So yeah, using the laws of logarithms first really cut down on the amount of work that we needed to do in this example. At the very least, it kept us from having to use the quotient rule, which is a win as far as I'm concerned. Okay, find f prime if f is equal to the natural log of the absolute value of x. So this is an interesting example because it goes into what I was talking about earlier with the antiderivative and the absolute value. So let's see. So notice, or rather recall, that by definition, hang on. How do I start a cases environment? Oh, I should have reviewed how to do this. One second. Wait, hang on. I can actually pause the recording, so maybe I should do that. I have returned. I have returned from the pause dimension. Okay, so absolute value. If x is positive, then the absolute value does nothing. If x is negative, then the absolute value reverses the sign. Well, how do you say reverses the sign symbolically? Well, you plop a negative in front of it. Okay, so that means the derivative of this junk is, if we've got log x, well, that's just 1 over x. Again, by definition. If it is log minus x, well, then we have 1 over minus x, then by the chain rule, times the derivative of minus x, which is minus 1. Oh, hey, look at that. The minus on the top and the minus on the bottom cancel. So, altogether, we get that the derivative of log absolute value x is equal to 1 over x for all values of x except for 0, in which case the natural log would give us negative infinity anyway, so it's not really well defined there. So for all x not equal to 0. So that means that if we want the antiderivative of x, you know, if we want the most general antiderivative of 1 over x possible, we should write natural log absolute value x instead of just natural log x. Because natural log x has the restriction that its domain is only the positive numbers. But when we write antiderivatives, like through indefinite integration, the convention is to give a function which has the biggest domain possible. So that would be with the absolute values, because that'll make the domain of the log as big as it can possibly be. It'll allow us to plug in negative numbers, in particular, because the negative is just going to get eaten by this absolute value, and then it's fine. So I just make a note of that down here. The derivative of log absolute value is 1 over x, and the antiderivative of 1 over x is log absolute value. So this latter thing is something that I really want you to remember. So the antiderivative of 1 over x is log absolute value x. Those absolute values do need to be there for this to be correct. And I'm making it seem like it's a technical point, which it is, but it really is necessary. Like I have a distinct memory of taking a graduate level class in differential equations not that long ago where, for whatever reason, we had to anti-differentiate 1 over stuff, and I forgot to put in the absolute values, and boy, it just caused endless problems. So trust me that those absolute values really are necessary when you're taking antiderivatives, at least. Okie dokie. So, what can we possibly do with this guy? Well, I mean, power rule obviously isn't going to work. Not to mention, it's not really the point of this section. So, the only other technique that we have under our belt at this point is U substitution. And it seems to me like it would be a good choice to take everything here in the denominator and just let that be U. Maybe, take the most complicated chunk of the integral and let that be u. That typically works. So let's do that with u equals x squared plus 1. What is the derivative? Because remember, every time you specify u, the next step is to take its derivative. What is going on? There we go. What's the derivative of x squared plus 1? That is 2x. Consequently, dx is equal to 1 over 2x du. Again, this is just the procedure for the substitution technique. So our integral is x on the top, u on the bottom, because x squared plus 1 is turned into u. And then instead of dx, we're going to put all of this stuff. Okay, so what happens? Well, we've got an x on the top and an x on the bottom. Those both cancel. We have a 1/2, which I can pull out front, because that is a constant. And all I am left over with is the antiderivative of 1 over u du. Well, how convenient that we were just talking about the antiderivative of 1 over u. It's a natural log absolute value. So then, the only thing left to do is to replace u with its original expression, x squared plus 1. That way, everything is in terms of x, as it initially was. Okay, now, one more really, really pedantic point. This is correct. This is completely correct. But x squared plus 1, that's always positive, right? You take an x squared, that's always going to be positive, or at worst, it's going to be 0 if it's 0 squared. But even if this is 0, add 1 to it, it's guaranteed to be positive. So you know what? The absolute values actually aren't needed here at all. The absolute values are redundant because this expression is always positive. Are redundant, I should say. So, not a big deal, but that is something that I should mention. Okay. What's going on here? Well, again, pretty much the only technique we have under our belt for doing weird integrals is substitution. And we should let the weirdest or most complicated chunk be our u. In this case, the most complicated chunk is the natural log here. So let's go ahead and let that be our u. Okay. Okay, so differentiate that. The derivative of natural log x is 1 over x, by definition. And consequently, dx is equal to x du. So move the dx up here, move the x over here. And this is a definite integral. So if you're doing the substitution technique with a definite integral, you have to change the bounds to reflect the substitution. So when x is equal to 1, that means u is equal to the natural log of 1, and the natural log of 1 is 0. When x is equal to e, that means u is equal to the natural log of e, and the natural log of e is 1, by definition, right? That's what we were saying up here. Where is it? Yeah, that's what we were saying up here. The natural log of e is 1, by definition. So our integral becomes Instead of 1 to e, it is 0 to 1. Natural log x becomes u. X is x. And then instead of dx, I'm going to write x du. Well, how convenient. These x's cancel. So we just have u du left over. And that is easy to anti-differentiate because that is just u squared over 2. We still have to evaluate that between 1 and 0, but that is also easy. Plugging in 1, we get 1/2. Plugging in 0, we get nothing. So 1/2 is our final answer. Okay, so earlier I mentioned that the antiderivative of cotangent is log absolute value sine. So what about the antiderivative of tangent? I mean, it stands to reason, by example at least, that we should get some expression involving the natural log as well. And indeed, that is what happens. So recall the trig identity that tangent of x is the same as sine over cosine. So that really what we have is integral sine x over cosine x. Now, why do I bring that up? Because now, maybe this is amenable to a u substitution. So in particular, let's let u be the thing on the bottom, because having things on the bottom in an integral is a cause for consternation. So let's let u be cosine x, and then hopefully things will work out. Which of course it will, because I've done this many times before. So the derivative of cosine is minus sine. So that means dx is equal to minus 1 over sine du. So that means our integral is sine over, okay, well now instead of cosine, that has become u. And then instead of dx, we're going to write all of this. And put parentheses in it because of that negative sign. So let's see. Negative sign, I can bring that out front. Sine x over sine x, so these two signs cancel. So we just have 1 over u left over. Cool. Well, we know how to deal with that. That just becomes a natural log. Natural log of absolute value. With that minus sign still hanging out. And then finally, to put it back into the original terms, replace u with its original definition, which was cosine. And there we go. And maybe I should put that in a box, because that is nice. That is nice to know if you ever wanted to know the integral of tangent. I mean, that's an elementary function, right? So we should know their antiderivatives. Okay. So, there is one more topic that I wanted to mention when it comes to logarithms and differentiation and anti-differentiation thereof. So you recall in this example up here, I have this ugly expression that would have required the use of the quotient rule, and the quotient rule, pretty much as a rule, is really tedious to work with. But this logarithm, if we used it to expand it out, then the differentiation became trivial. So, maybe if I have some big ugly expression and I need to differentiate it, if I differentiate the logarithm instead, that would be way, way easier. Well, let's codify that into a technique, namely the technique of logarithmic differentiation, or using the laws of logarithms to make differentiation easier. This is a technique that's used a lot, for instance, in statistics. If you ever take an advanced statistics course, the sort of functions that you're looking at there are extremely ugly. So a common technique is to look at the logarithms of things instead, because then you can use the laws of logarithms to expand things out, and that just makes things tremendously easier. So let's go through these 3 steps with the example at hand. So differentiate this big ugly mess. Okay. First, take natural logarithms of both sides and then use the laws of logarithms to simplify. Okie dokie. So natural log of y equals natural log of all this junk. Okay, well let's go through it. Let's go through it quickly. So exponent, bring that out front. Log x. Multiplication, that becomes a plus. Square root, that is an exponent of 1/2, so we can also bring that out. X squared plus 1, nothing we can do about that. Division, that becomes a subtraction. Power of 5, bring that out front. And then 3x plus 2, nothing else we can do about that, right? Okay, so we took the log of both sides and used the laws of logarithms to expand this dude. Next, differentiate implicitly with respect to x. So just differentiate both sides. So what's the derivative of log y? Well, that is y prime over y, right? I mean, let me remind you. I'm just using this rule here. Instead of f of x, we're now calling it y, so it's y prime over y, right? Because y is a function in this notation. So differentiate both sides. So that's the left side. What's the derivative of this? Well, that is 3 over 4x, because the derivative of log x is just 1 over x. Let's see. So that 2 is from the 1/2. So we have derivative of x squared plus 1, which is 2x, over x squared plus 1. And then we may as well cancel those 2's. Derivative of this dude is, so let's see, derivative of 3x plus 2, which is 3, over 3x plus 2. And then 3 times 5, may as well combine that to make a 15. Okay, so there's that. And then 3, solve the resulting equation for y prime, because really that's what we're interested in, right? We want the derivative of this thing that we started with. And that's easy enough. To get y prime by itself, just multiply both sides by y. So y prime is equal to y times all of this. And it's a little bit uncouth to leave the y in here. Really, we want the final answer to be entirely in terms of x's. But thankfully, we already have an expression for y, right? It was given to us at the very beginning. So let's just replace y with all of this. And then we shall be done. Then, of course, we still have all of this junk hanging out right next to it. Whew. So that is tremendously ugly, but not too much of a pain to actually derive, since we used the laws of logarithms to sort of smooth out all of the roughness. So yeah, that's the technique of logarithmic differentiation. This is a problem that they like to put on exams, like in the final exam, for instance. There's almost always a problem like this. So this one is worth remembering for sure. Okay, so that's it for this lecture.